good afternoon, and welcome to this day's Nano Seminar. Today we also have master students from here that will give their talks. And first up is Mikhailo Savitsky, who has been working with Ilari. And you will tell us about fabrication of 3D phononic crystals. Yes. Yeah, please.
Thank you very much. Good afternoon, everybody. Today I would like to present my master thesis work. The topic of this work is fabrication of 3D phononic crystals for thermal transport management. My name is Mikhailo, and my supervisor is Professor Ilari Moasilta. So the first question which arises after this topic is, what is this phononic crystals? So phonons, it's mechanical vibrations responsible for the transmission of everyday heat and sound. So what is phononic crystals? Phononic crystals is artificial materials which are pretty similar to photonic crystals, but they are designed for acoustic waves instead of electromagnetic waves. So they can be one-dimensional, two-dimensional, or three-dimensional. They are designed to have periodic inclusions of material with different elastic properties from the media they are located in. So they are interesting because of their feature, which is called band gap, so in dispersion relation. So this band gap means that not all frequency waves can propagate through these phononic crystals. And the frequency of these waves and its corresponding wavelengths is the same order of our size of our periodic inclusions in our structure. So we can see we can fabricate by making higher periodicity size for sound or hypersound or even heat. So the heat thermal excitations at room temperature is the order of terahertz range. And so it corresponds to angstrom and nanometer size of periodic inclusions. However, we can cool down our sample to sub-millikelvin range. And in that case, the heat excitation frequency will be in gigahertz range. So which corresponds to the periodic inclusions of the order of few hundred nanometers. So in that case, by having complete band gap, we can see some kind of reduction of acoustic waves, which is also heat waves transmission. So the motivation of the work is that theoretically, the magnitude of this control, heat transport control in 3D structure is bigger than in 2D structure and 1D structure. So the question arises here, is it possible to fabricate the desired 3D phononic crystal structures? And if it's possible, how? How exactly? So we started from theoretical simulation by using finite element method. So the simulation was provided by Dr. Thomas Portinen. So it was designed that we have the structure from periodic inclusions redesigned to be silicon dioxide colloids with the diameter d. And they form FCC lattice by contacting to each other with diameter d. So by having really like hard contact, we can see the size of our band gap here is bigger. So, and this band gap for the structure is within gigahertz range. So basically, we should receive noticeable decrease in thermal conductivity in these structures. So now the question arises, how to fabricate this sample? First, we should start from sample preparation. So we cut our silicon chip. It was pure silicon, naturally oxidized, and we cut it in these dimensions. And then we put it into oxygen plasma treatment for some time in order to make it like non-conductive electrically and to increase its hydrophilicity. It's important for a next step, which is called deposition nanospheres. So our periodic inclusions, which will form our 3D crystal lattice, consist of this silicon dioxide 170 nanometer sized colloidal crystals. And initially, they are in low concentrated aqueous solution. So our spheres are in this aqueous solution, approximately 5% concentrate. So by using single-step vertical deposition method, we dip in our chip and then slowly dip out, which yields in self-assembled close packing crystal 3D nanostructure. So in this picture, it's presented the home-built setup which was used for this dipping. Here we can see it's a bottle with our solution, silicon dioxide spheres in water. Here we can detach our sample chip and dip in and dip out very slowly by controlling this. Also, it's very important to keep our chamber clean and to control the humidity. So here you can see this controlling humidity and evaporator and also the fan. So, and as a result of our dipping, we received this close packing FCC lattice structure which consists of silicon dioxide spheres. It's a top view made by Sam. Also, we managed to fabricate different thickness of this structure. So here it's presented low, thin, medium thickness, around 10 layers of this silicon oxide spheres. And it's also possible to make it even thicker, depending on the parameters. So first, parameter which we can control the substrate surface. I mean, it's hydrophility, which is really important because our solution is in water. Then it's humidity because this self-assembly is based on evaporation process, dipping speed, and of course solution concentration. So after this making actually the structure, so we already are successful in fabrication this 3D crystal nanophonons on the chip. Now there is a question how to measure the thermal conductivity in this sample. So for that reason, we need to fabricate thermometer and heater on top of the structure. So in order to do it on our rough nanosphere structure, we need to coat it to smooth the surface with some thin layer materials. So we already tried physical vapor deposition, plasma-enhanced chemical vapor deposition, and atomic layer deposition by coating with thin layers of silicon oxide and aluminum oxide. However, the results were not successful. So here we can see that at the last step in electron beam lithography, after metal deposition, it was called lift-off process in acetone, our spheres with coating layer was detached randomly, and the structure, the thermometer, was broken. So after that, we tried another material for coating, which is called negative photoresist SU8. And we found it's a promising material. Initially, in liquid phase, we coat this thin layer initially in liquid phase and then exposed to UV to make it hard and stable to acetone, so which is really important for this electron beam lithography deposition. However, this doesn't solve the problem with cracks. So here you can see AFM image where silicon oxide balls are covered with this thin layer of SU8 negative photoresist, and we still have these cracks which are always present in all process which involves drying. However, we can try to control to minimize this effect by making the structure thinner. So the next step, after we are successful in coating this surface and making it smoother, we can fabricate our thermometer and heater. It's represented by this NIS tunnel junctions, which stands for normal metal insulator superconductor tunnel junction. By using angle operation, we fabricate two NIS, which yields in one thinness junction, and the size of one thinness junction was designed to be 500 nanometers by 500 nanometers. So here is a picture of successfully fabricated this NIS junction on top of 3D phononic crystal coated with SU8 photoresist. So here you can see this tunnel junction here. It's SAM picture and AFM picture. The surface is really rough, but these junctions are working. And the thickness of this, the size dimensions of this tunnel junction is a little bigger than it was designed, basically because of proximity effect during electron beam lithography. And the bottom layer here, it's aluminum, which served as superconductor. Then it was oxidized to create aluminum oxide insulating layer, and the top layer is copper, which stands for normal metal here. So here it's summary of the fabrication process. So at this point, we fabricated successfully the sample, which has on top of this 3D crystals, phononic crystals, coated with thin layer of negative photoresist, and with, on top of this with 2 sinus junctions. So now we can start to check if there is a reduction in thermal conductivity as we predicted this theoretically. So for that reason, the preliminary measurements were conducted. So by having this geometry, as was taught before, the first sinus junction, so one NIS junction and second NIS form sinus junction, and the first one was served as thermometer, and the second one was served as heater. So we tried to measure the response of this heater and to measure the temperature, response temperature of this heat transmission by measuring this in Faraday cage, by using helium-3, helium-4 dilution fridge, refrigerator, and cooling down to 40 millikelvin. So firstly, the sinus IV characteristics were measured in order to check if it's working and how properly it works. So here we can see the size of superconducting band gap, and it was done for different temperatures. So this is sinus IV characteristics correspond to classical IV characteristics with also density of superconducting density of states broadening. So ideally, here it should go to 0 straightforward. But of course, because of this broadening, we have some current at these voltages. And also by having higher temperature, we can also have this high energetic normal electrons. So of course, in order to use our sinus as a thermometer, we should calibrate it. So we measured the voltage across the sinus versus temperature, best temperature, for different bias current. So for the smaller bias current, here it's presented, 0.051 nanoampere. We can see this red curve, it's experimental data, and the two others, it's theoretical fit based on BCS superconducting theory. Here you can see it fits pretty well. However, for a higher bias current, 0.97 nanoamperes, the experimental curve, which is presented by black curve here, doesn't fit so well with theoretical. So probably the reason is because our sinus, it's not so symmetric, so two different NIS junctions.
What about the heating of the junction, of the island? By the bias current?
So the heating was, the measurement for the heating was done for at this bias current.
No, but this is a thermometry, right?
Yes, so it's a thermometer.
Yeah, but does it matter if this bias current heats the sample? But maybe it's a small effect.
It's too small and it's pretty far away. So after that, we were able to measure, actually, to conduct this thermal conductivity measurements. So we measured the heat power, the power emitted by a heater versus temperature response on our thermometer. And it was approximated to this formula, so we can see this power of force. So we can say that theoretically it predicted that for regular phonons by theory for low temperature, the thermal conductivity should be proportional to temperature and power to 3. And versus yields in the power heat emissions is proportional to the temperature and the power of 4 for regular phonons. So here we can claim that the only phonons were responsible for heat transport. So as a result of our work, the first sinus junction with contact pads were successfully fabricated on top of thin medium thickness silicon dioxide spheres layer, which serves as 3D phononic crystal. And the proof of this was successfully measured and approximated by theory IV and VT characteristics, which was able then to conduct some preliminary thermal conductivity measurements. However, we cannot claim and what how strong the reduction of thermal conductivity we achieved, because we still need to fabricate the sample with the same geometry of heater and thermometer in order on a surface without 3D phononic crystals, in order to compare thermal conductivity for these two samples. And also, of course, there is still maybe space and time to improve our fabrication techniques, and maybe to use another geometry in order to conduct and repeat the thermal conductivity measurements. So thank you everybody for your attention, and I would like to thank people that helped me a lot, especially Andrei Torgovkin, Yaolan Tian, and Dr. Thomas Poitinen, and of course my mentor supervisor, Professor Ilma Silta. Thank you very much.
Let's see. It's open for questions. Let's see. Do we have a question somewhere? Here we have one.
So the last measurement was so that you had the heater and the thermometer operating at the same time, I guess.
Yes.
And then you measure the temperature induced by the heater to the thermometer, right?
So here we have a heater. We
And
like applied here current.
would be nice to see the bare data. I mean, because you now already have kind of the final data
Yes,
there. So how large is the temperature change in the thermometer due to the heater, for example?
So here is the change in temperature of thermometer presented here. So it was around 200 millikelvins.
So this is heating.
So this is a temperature of the thermometer, which was measuring actually this heat transport from heater.
I see. Okay. That's okay. I see.
Bath temperature is low.
Yeah.
So it's not bus temperature, it's actually the temperature of our thermometer, not heater.
And then you have some heat. I mean, some prefactor to this dependence, which you can get from here.
Yeah, I mean this.
It's probably there, but I guess it's A. Or
Yeah.
Yeah. Does it tell something?
I suppose not at this point. So there still should be some kind of theory, because we cannot predict how. The problem is here that we still don't have a theory which tells us how exactly here is emitted. So it's emitted in all the directions. So we don't have a theory and model which will calculate and tell us what fraction of this heat is going actually in this direction. Because we have pretty thin structures, so maybe a lot of heat goes just directly into substrate.
Okay.
So at this point, this prefactor, it's hard to say what actually the meaning of this prefactor is.
Okay. Thanks.
That's why we need the control experiment.
Yeah.
Prefactors don't matter. So.
Sure.
Do we have any more questions? I have a question.
Yeah.
Have you considered doing the fabrication the other way around? Put the heater and thermometer first, and then put the...
Yes, actually, I thought about this, but in practice, it's impossible because NIS junctions, the tunnel junctions, are extremely fragile. So they can be broken and shortened easily from some small charge. So it won't survive all this following fabrication process. So that's the point. It's impossible to do.
Right, because you have this SU8 layer in between, which also
Yes, so
alters your data somewhat.
of course it affects. So theoretically, model was designed to have the silicon oxide spheres in vacuum media. So of course, in this case, we should maybe have smaller band gap by using SU8. But at least we should be able to observe some reduction of thermal conductivity in this case.
Any more questions? Here? Yeah.
On this image, we see that the grain boundaries are perpendicular to the heat transmission direction.
You mean this?
Yes. Was this a conscious choice to put the thermometer and heater perpendicular to the grain boundaries, or by accident?
Honestly, it was done by accident at this point. because this is cracks which I told about, and they were coated with thin layer of SO8. So it's the main reason why usually we were not succeed in this working thermometer and heater, because of these cracks which can be seen here. So we need to coat it with something, and after coating it actually doesn't matter really in what is arranged here. And actually here it's just accidentally arranged like this, because usually we have random arrange of these cracks. Of course, but here we can see that the dipping was done in this direction. So it's maybe the reason of these cracks, exactly vertically.
The question would also be that do you expect the direction of the cracks influence the measurement? So if you measure the heat transmission parallel to the cracks, so if you had this thermometer and heater like 90 degrees shifted, like
Yes, so we
rotate.
actually discussed this, so probably we still need to conduct the measurements where we put this heater just very close here and in this direction. So it still would be really nice to measure in this case also the geometry.
One question more. Have you thought about this laser direct writing method? So 3D laser printing, which I think this 170 nanometers is at the moment also in the maximum resolution scale for this kind of method. So you could print your structures and maybe a little bit more easier than to use this self-assembly, which is very prone to cracking.
Yeah, but here we have the bottom layer, it's aluminum, then it was oxidized, and the top layer is copper. So I'm not familiar with this 3D laser.
Resolution is not enough.
Okay.
That's
So-
the few hundred nanometers is the absolute sort of smallest thing. So here we kind of need contacts that are like 10 nanometer scale.
Okay.
So yes, we are planning to do it like in a larger scale.
Okay.
Okay, I think we have to wrap here and move to the next speaker. So thank you.
Mhm.
Thank you.
Thank you very much.